Welcome back to the second class. It was made clear to me in the hallways that in the previous recording I was not my usual enthusiastic self, and it was recommended that I would wear an interesting hat or something. So here we are. Now, hey yo, dickety dogs. Let's talk about what we're going to talk about today. We'll talk about research methods. The reason I do this is, first of all, it's a chapter in the textbook. I think it is worth revisiting. Bear in mind that this is really hot. I'm sorry, I can't do it. It also was a really good match for the bow tie. Important material. Some of you have taken what is now 2713, but 313 research methods. It's a while ago you took that. I think it is good to refamiliarize yourself with some of that material. Because this is a psychology course, it is very much based on empirical science, and as a result we're going to be describing experiments, and you need to have some terminology pinned down. And bear in mind, in this particular field of studying learning, there actually are some specific research designs that you see quite a lot that are not your run-of-the-mill experiment. So that's why I want to spend some time on this. Let's see what we can do. We're going to talk about some of the accurate terminology for describing research, as well as how to measure behavior. We'll talk about how you can measure various types of behavior. We'll talk about some descriptive methods, experimental methods, and we'll talk about appropriate research designs for various research questions and situations. If you feel, we'll have to address animal research. If you feel that you're very comfortable with research methods, that's for you to judge. It will be on the exam, so I would recommend quickly going through the slides, and if you see something you think, I'm not really familiar with this term, maybe watch this part of the recording. If it really is a while ago that you took 313, it might be good to watch the whole thing. Again, I'll try to keep these as short as I can, but do what you think is best. Okay, here we go. So starting off, the absolute basics, and I'm going to be very fast here because at this point in your studies, even if you are a second year student, you should have heard this kind of story a couple of times. So we measure variables. Variables are things that can vary. So it could be a person, could be a place, could be a thing, something that changes over time, and something that can have different values. So intelligence is a variable, but also a pigeon in this course, a pigeon pecking, that's a variable too, because it can peck more times or it can peck fewer times, and that's a variable, right? We have independent variables. Simplest definition, that what is manipulated. That is an independent variable, and they are made to systematically vary across typically different conditions of an experiment. Could be 2 conditions, 5, could be 10, whatever. If there's only one condition, then it's not an experiment, because you need a control condition to have a true experimental setup. And then you have the dependent variable, and you may remember, at least I definitely found that as a student, when I learned these terms, I found them very confusing, because I always thought dependent, isn't that dependent, like why is that dependent? Well, dependent variables are the variables that you measure, and they're called dependent variables because they depend on the independent variables, the different manipulations in a study. And then there is the assumption that there will be a functional relationship, that is a relationship where changes in the independent variable then result in corresponding changes in the dependent variable. If a rat is hungry, he'll eat more. If a rat is not hungry, he'll eat less. Right? So that would be a functional relationship. A very simple one. Stimulus response, don't you ever think? Yeah. Well, a lot of this course is rooted in the idea that stimulus response learning is very vital to human psychology, and for that matter, animal psychology. So we'll talk about that a couple times. A stimulus in this context is really any event that can somehow influence behavior. And in the context of learning, studies, we distinguish two things. There are appetitive stimuli and there are aversive stimuli. And those names are really fairly intuitive once you've learned the definition at some point. Okay, so an appetitive stimulus is an event that an organism will seek out, like food. Appetite, right? So anything that you like, and some things are naturally rewarding. Think of food, think of water, think of sex. These are things that typically are, to an organism, rewarding. Especially with sex, I know there can be some exceptions, but that is studied in this field of research that we'll talk about. And then you have aversive stimuli. That's the opposite. An aversive stimulus is any event that an organism will avoid. So think of electric shock. So we're not going to start with operant conditioning. We'll start with classical conditioning. So that's really sort of stimulus and a response. But I'll give you a simple example from operant conditioning. A rat presses a lever. Yes, I will say lever. When that lever gives the rat food, he's going to press the lever more, provided he's hungry. If that lever press gives the rat a shock, he's obviously going to press the lever less, because it's aversive. It's not pleasant to the rat, right? So that's how you should look at that. And then there is a response. The response is a particular instance or a unit of a behavior. I've just given you one. A rat pressing a lever, that's a response. A rat running through a maze, that is a response. A rat eating or drinking, that is a response. And we can distinguish overt and covert behavior. Overt behavior is the simplest. That's behavior that can be observed by anyone. And if you want to be a psychologist, that's a fantastic way to learn. Go to the food court in the mall on a Saturday afternoon and look. Observe. That's how you learn about human behavior. See what's going on in the lives of other people. It's very interesting. But you can observe that stuff, what they do and what they say, because that is overt. But there's also covert behavior. Covert behavior can really only be observed by the person performing the behavior. So if someone says, let's say, dreams of dating Scarlett Johansson, you do not know about that unless they tell you. And humans can tell you about such things, but animals cannot. So if you do animal research, studying covert behavior is actually a bit more complicated than studying overt behavior, right? Because they can't tell you. So you have to use really clever research designs to study covert behavior in non-verbal animals. And we'll see some examples of that in the course. Now, if you look at a person like Skinner, who we had talked about last time, he's not interested in covert behavior. Right? Not really, because I mean, you can't observe it, so what's the point? Right? Whereas someone like, say, Freud, who will not come up in this course, but Freud was very, very profoundly interested in covert behavior. Secret desires and dreams and that kind of stuff, right? So it depends a bit on what sort of tradition in psychology you cling to. Okay, so we have behavior, we have stimuli and responses. What about motivating operations? Motivating operations are procedures that change the effectiveness of a stimulus or an event as a reinforcer or punisher. So in other words, motivating operations alter how appetitive, desirable, or aversive, undesirable, a stimulus is. I'll give you examples because I know that can be a little abstract. We distinguish two processes. There are establishing operations, and establishing operations increase how effective a specific event is at reinforcing or punishing a behavior. So, for example, if you restrict the amount of food, let's say a rat can eat, that is an establishing operation because it evokes a state, namely hunger. You have created that by not allowing the rat to eat a lot. Then there are abolishing operations. Well, I hope you can see where this is going. That's the opposite of an establishing operation. An abolishing operation decreases how effective an event is at reinforcing or punishing a behavior. So, for example, if you feed an animal to satiety, so you just feed them so much that they're not hungry at all, well, then you have abolished hunger. So the hunger is now gone, therefore you have abolished hunger. And sometimes I find that people find this a little confusing, because you could say, but establishing operation, like isn't it establishing because you give an animal food? No, because that is you doing something. The abolishing part comes in what you do in the animal. So you may give the animal a lot of food, but you reduce its hunger. You may give it a lot of sugar water so it drinks to satiety, it won't drink anymore. Now you have abolished thirst. Right? So abolishing operation, establishing operation. Let me know if that distinction is not clear to you. Two terms that are important, and that in everyday English language people kind of use interchangeably, are contiguity and contingency. But in learning research, those terms have very specific meanings. Contiguity means that something occurs close together. I shouldn't say something, that two things occur closely together. And they can distinguish between temporal and spatial contiguity. Temporal means time, right? So temporal contiguity means that you have two events that occur close together in time. If I flick a light switch, the light turns on. Not half an hour later, but immediately. Light switch, light. That is temporal contiguity, because these two things occur closely together in time. And then you have spatial contiguity. That refers to events that are situated closely together in space. Now, that can be a little bit tougher to picture, but look at this. If someone knocks on your front door, there is close spatial contiguity, because the knock you hear comes from your front door, so you know exactly where to go. But if someone rings a doorbell, there is less spatial contiguity. There used to be, I remember this I'm now going way back in time. My grandparents had this old house from the very early 1900s, and they had a camel bell that actually came from somewhere in Saudi Arabia that was over the door, and there was a thing in the door, outside the door, you pulled, and then that bell would ring. There would actually be a cord attached to it. Very interesting, old-fashioned European technology. But these days, doorbells are largely electronic. And then you have a little box with a doorbell, and that box could be anywhere. It could be in your bedroom. It doesn't have to be right next to the front door. So now, if your doorbell has that situation, it does not have high spatial contiguity, because the bell button is next to the door. That box could be in the basement or in the attic, so to speak. Completely different. No spatial contiguity. I hope that makes sense. For my grandparents, there was complete spatial contiguity, right? Because the bell and the pull were very close together spatially. Okay, so that's contiguity. And then you have contingency. Contingency means that there is a predictive or a functional relationship between two events. And that means that the occurrence of one event will predict the probable occurrence of another event. So, for example, if I blow a puff of air into your eye, you're going to blink. That's a contingency. I can predict that is almost certain to happen. And that is research that people do. And you will see in this course, that is what actually has been done. They do that with rabbits. So it's a type of conditioning. That is contingency. I do this and you do that. Very likely. But you can also become habituated. You can also become less likely to do that if it happens all the time. I hate that stuff I do in the eye doctor. I have a very sensitive blink response. Nothing I can do about it. So I hate when they blow air in my eyes. But if they do that 20 times in a row, at some point you'll barely blink anymore, because you know it's kind of, that you've habituated to it. Habituation, sensitization will come up in a later class. Okay, I hope this is clear. So then let's move on to how you exactly measure behavior. Well, the first step, and this sounds kind of like kicking in open doors, but it's important to think about this. the first step is you have to define it. And we call a proper experimental definition, maybe I shouldn't say experimental, a proper research definition, an operational definition. You cannot write in your paper, and we tested some pretty depressed people. That's not an operational definition, because the reader will not know what you mean by depressed. They will not know how you measured that. So you could say anyone who scored, I'm not a clinician, who scored higher than 10 on the Hamilton depression scale, however that scale works, I know it's real, I just don't know what its scale is, was considered depressed. And now the reader knows, okay, so this questionnaire, this score, that for these people meant depressed. Right? That's an operational definition. The second step, of course, is to record it somehow. Now, when it comes to recording behavior, and again, bear in mind, for this particular course, we'll look at a lot of animal research. I'll come back to that, but a lot of research done with rats, with pigeons, with quail, so you record behavior. It can help to think a little bit about what those animals would do. So the first thing, maybe the simplest thing that you can record is rate of response. And rate of response simply means the number of responses that happen in a specific period of time. So you put a rat in a operant chamber, the Skinner box. You have the rat press a lever, and every time it presses the lever, it gets food. And then you measure, okay, in 60 seconds it pressed the lever 130 times or something. That's rate of response. Then you have intensity or magnitude of the behavior. Think of how loud someone is shouting. That would be a human thing. But for rats, you could measure, do they just lightly tap a lever, or do they really like force it down? That would be intensity or magnitude. Then you have speed. Well, the length of time it takes for some sort of continuous behavior to occur, start to finish. So how long does it take you to read a 20-page chapter in a textbook? Well, it depends on the textbook, depends on the material, depends on the font size, how many pictures. Well, I get all that, but theoretically, if you give everyone the same text, how long does it take them? Well, that's their speed. Their reading speed will be higher for some people, lower for other people, right? That'd be speed. And then finally we have latency. Latency, I think these first three are all kind of obvious based on the names. Latency can confuse people a bit. That simply means how long does it take for something to start? In our case, for this course, mainly behavior to start. So how long does it take you to leave your bed to actually get up when your alarm sounds? Right? That would be latency. I just have to blow my nose here. Sorry. It's cold out. Okay, so I'm eating a tissue. Oh, God, the things I do for you people. Now, I feel like I should now cough it up like a cat or something. Okay, how long does it take for Dr. Brown to cough up the tissue he just swallowed? Okay, now that would either be speed if you measure how long the process takes, or it would be latency if you measure how long it takes for me to start coughing. What a brilliant illustration. As you can see with me, what you see is what you get. It happens online, it's not edited out, and that's how you learn. Okay, so that's latency. Latency is used in other ways too, right? Like if you've taken 4705 with me, we've talked about EEG research. You look at event-related potentials, so specific brain waves. You can measure how long it takes for them to peak. That also is latency. Okay. So then, how exactly do you measure things? Well, different tools have been developed. I'm a cognitive psychologist. We use a lot of reaction time research. That means there are specialized programming languages like presentation or E-prime that are meant to be used on a computer. They display stimuli at a very precise rate, and they measure reaction time down to the last millisecond. Millisecond, 1/1000th of a second. So very, very accurate. But back in the day, especially Skinner, right? Skinner was very interested in rats and pigeons, and let's say how often they pressed levers. He developed a device called a cumulative recorder. Skinner, at least that's what he used. Skinner was a bit of a sort of an inventor, tinkerer type guy, so he has this thing, and that's what you see Let me get my pointer out. Sorry, that's what you see right here. So it's kind of old-fashioned. You have this device which has a pen attached to it, and then there's a roll of paper that's just pulled out by a machine, and then you have that pen that's going up and down. Think of what they use to what you call that, like seismic stuff for earthquakes, that what you see in movies, that sort of stuff, or even like old-fashioned heart rate EKG monitors did that too. So I'm sorry, I'm not actually sure if Skinner invented this, but this is what he used, and it sounds like something he would hook up to his devices because again he liked to fiddle with equipment. So in a machine like this is called a cumulative recorder. It's called cumulative because it cumulatively records responses. It keeps going and recording and recording and recording, and it's always a little complicated because the paper moves in this way, but then you read it that way, right? So the paper goes in that direction because it's pulled out that way. That pen does these things, but you read it the other way around. So here you can see, and we'll see the actual experiments this is based on in the course. But I mean, here you see an animal. It's not responding because this is a flat line, and then there is a bit slow responding, and then these dashes. That's when a reinforcer, so a reward, but you should really say reinforcer, was given. And then you see that once the reinforcer is given, the animal starts to do more, like press the lever more, because now when it presses a lever, it knows that it gets a response. And you see another reinforcer is given, another one, and you see that the line becomes steeper. Still eating tissue. Line becomes steeper, so that means the animal is responding faster, right? And again, then all these dashes, those are reinforcers. You can also do different research with animals. So here we have a rat. Last time, you remember we talked about Tolman, that very important experiment with rats being reinforced or not reinforced or suddenly reinforced while they ran through a maze. Well, here you can just measure speed, right? So this is a matter of rat is put down, stopwatch, click. How long does it take for the rat to get to the food? Or go into the left arm or the right arm of a T maze, or run in a straight maze, run from one end to the other. So that's kind of stuff we're talking about these days. A lot of this is computerized. It's done with infrared cameras, which is much less sensitive to researcher bias than the researcher actually clicking a stopwatch, because when do you do that? I'm not saying people cheat, but they have shown that those kinds of behaviors are very sensitive to researcher effects. So they do all that really nicely. Infrared cameras, it's great. Okay. Now, there are different ways in which you can measure behavior. So one thing you can do is interval recording. You simply measure within, let's say, a series of continuous intervals how often behavior occurs. So you can say, for every hour, I put a check on a checklist when I've had a glass of water or smoked a cigarette, or like whatever behavior you're observing, how often a child cries or whatever. You say, within this hour, how many times does it happen? Okay, next hour, how many times does it happen? Okay, next hour, etc. You can also use time sample recording. And time sample recording means that you now have discontinuous intervals, and then you measure in those discontinuous intervals how often a behavior occurs. So for example, you can have a classroom where you're observing children. If you use interval recording, you sit down in that classroom with your clipboard, and every time a child, let's just say, raises their hand, you write that down. Yes, once, there's another one, twice, three times. That's interval recording. But if you sit in that classroom and you just say, now an interval starts, and then for 10 minutes, you check how many times kids raise their hands, and then you don't do anything. And then another 10 minutes, but that could be half an hour later from the first 10 minutes. So it's not continuous. That's what's meant by discontinuous. Or maybe it's clearer to explain it this way. You have a school. Let's say you have 3 grade 5 classrooms. You walk into the first classroom, 10 minutes, you observe. Leave, go into the second classroom, 10 minutes, observe. Third classroom, 10 minutes, observe. Go back to the first classroom. Go back to the second. Maybe you don't do it in order. You go 1, 3, 2, 2, 1, 1, 2, 1, 3, 1. That kind of stuff is time sample recording. Has the advantage, it takes less time. Has the disadvantage, you may miss out on things. Because if you're in just the wrong 10-minute window, it doesn't have to be 10, right? It could be 5, could be 30 minutes. If you're in the wrong way, you may miss behavior, right? But it's more economical. Then you have topography. Topography, that sounds maybe like a slightly weird term in this context, but that simply means observing the physical form of the behavior. Think of a rat pressing a lever in a Skinner box. It can do that in different ways. It can use its right paw, it can use its left paw, it can use both paws, it can use its nose, and it can even use its tail. All those actions, all those behaviors will press the lever, right? So no matter how it does it, the behavior is the same, namely a lever press. That's important, and sometimes that matters. Sometimes researchers only want to count a lever press if it's done with the right paw, because that's part of the conditioning, or only with the left paw, or only with its nose, or whatever. And that's topography. That's the physical form of the behavior. I hope that's a clear explanation. Okay, sorry, I had to restart this part of the recording. I was trying to move my face out of the way, but I could not, so I'm just going to have to do this. So I don't know what exactly was kept of this recording, so I'm going to say this. How do you know, sorry if I repeat myself now, but I'll be quick. How do you know if observations are accurate? How do you know? Okay, well, these days you can measure a lot of things with computers, like reaction times or infrared cameras, that kind of stuff. Back in the day, researchers used to observe behavior. And then how do you know that they're correct? Well, assuming that they're not lying, we'll just work on the premise that scientists are honest. That's not always the case, but just for simplicity's sake, there we are. How do you know? Well, you can have multiple people rate the same behavior and then calculate something called inter-observer reliability. We'll spend a little bit of time on this in the interactive class, but for now, inter-observer reliability measures the degree to which two or more coders agree. And statistically speaking, you have, for the stats friends, you have different measures. There's Cohen's kappa, there is Kendall's W. Usually we say about 80% is an acceptable minimum and about 90% is desirable. If it's more than 90%, that's really good. You calculate this kind of stuff in its simplest form as the number of intervals during which observers agree divided by total number of intervals. So unfortunately, my face is blocking half of this table, which is unfortunate, and I can't move that thing. So I'm just going to talk you through it. We have to adjust the calculation, but follow this calculation on the slide without my face on it, and then you should be able to get to 83.3%. But I'm now going to pretend there are only 8 trials because the rest of the trials are blocked by my face. So in trial 1, the two observers say, yes, the behavior occurred. Let's say it was aggressive behavior in rats. That's a bit like a child raising a finger. Everybody's going to agree 100% of the time because you can see it, right? But with rats, are they really aggressive? Are they not? So let's go with that. That's what they've coded. On the first trial, the observers say yes. On the second trial, they say no, there was no behavior. On the third trial, they say yes, there was behavior. On the fourth trial, observer A says no, but observer B says yes. This is a disagreement. Up to this point, they've agreed. This is a disagreement. Likewise, trial 5 is a disagreement. It's a disagreement because one says yes, that's observer A. That's observer A, and one says no, that's observer B. On trial 6, they both agree. They say the behavior is there. On trial 7, they say it's not. And on trial 8, they say it is there. So there are 8 trials. In reality, again, 12. Do this calculation at home. See if you agree. But for now, this would suggest that we have 1, 2, 3, 4, 5, 6 out of 8 trials where the observers agree. Well, 6 divided by 8, that's 75%. So the agreement is 75%. That's a little below the acceptable minimum. What do you do in such a case? probably give the observers more training. Explain to them more what they're looking for. Aggressive behavior in rats looks like this. Now recode. See if you still agree. Okay, that's how you would handle that. All right, I am going to turn this off and we're going to move forward. Okay, my slides are no longer moving. It's just wonderful. Okay, magically I've managed to, I think, move forward. Here we are. Let's talk about some research designs. There are different research designs. So we have descriptive research. There you just study behavior as well as the circumstances within which the behavior occurs. A naturalistic observation, that means you really systematically, because it is science, observe and record occurrences of the behavior you find interesting within the natural environment. And my favorite example is you want to figure out how parents handle screaming kids. You don't bring them to the lab. You go to Walmart on a Saturday afternoon and you just observe. You know, parent scold a child, parent whatever. Like, that's naturalistic observation. Then you have experimental research. Experimental research tries to identify functional relationships that we're interested in through manipulating the independent variable or variables and assessing the effect of that manipulation on the dependent variable. So now you could say, I bring parents to the lab, I see how they interact when their kid gets upset. Now I give them a training, I bring them to the lab again, the kid gets upset, I see if their behavior has changed. That would be an experiment. Now I've manipulated something, and it's within subject design, so there is a baseline that is kind of the control condition. Then you have group designs. In group designs you have one or more independent variables or levels of independent variables. Remember, a level is kind of like a condition, right? So if you give people chocolate, or what else do we have? It was just Christmas. A candy cane or just a placebo. These are three levels of one independent variable. Yep. They're manipulated across groups in a group design. And the effects are then compared across the average performance of each group. So I check reaction time if you've had chocolate. I check reaction time if you've had a candy cane. I check reaction time if you've had a placebo, either with the same participants within subjects or different participants between subjects, right? A simple control group design, that is as simple as it can be. You have an experimental group and a control group, and you randomly assign people. Like basically not a coin toss, a coin toss. Flip it, you go experimental, you go experimental, you go control, you go experimental, you go control, etc. Right? So that's it. And then you have comparative designs, which are interesting, and we'll talk a little bit about that near the end of the course. Comparative designs compare different species. So now species is an independent variable, and you can see how, say, chimpanzees and and toddlers, human toddlers, how they handle a certain task. That's a comparative design. Okay. Okay, so there are pros and cons to all these designs, and really, like, you need a full research methods course to dig into all that. But I mean, you've either already done that or you will do 2713 at some point. So for now, group designs have certain pros. A pro is functional relationships can be identified through statistical tests. So you have a very solid way of finding things out. But there are cons as well. One of them is you require larger numbers of subjects or participants. Subjects we typically reserve for animals, participants are human beings. Another downside is you tend to focus on average performance, not individual results. Right? If you've taken statistics with me, you know exactly what I'm talking about. You have two groups, you average performance in the two groups, and you compare them statistically. But at no point do you look at individuals within that group. That's not very common. And that means that those results are not necessarily representative of an individual. because we assume that most data are normally distributed, so there will be a lot of people scoring close to the mean, but there will be outliers on the left and outliers on the right. Often these kinds of experiments get analyzed and interpreted only at the end of the experiment, and that need not be an issue. But what if you're trying to evaluate a new intervention method for people with depression? It would be nice if a week in, 2 weeks in, you'd be able to say it seems to be working. Because if you do this for 6 weeks or 8 weeks or 12 weeks and then you find out it didn't work, that's a lot of time wasted, right? But in principle, you can't do that. You can't look at that time. And there are reasons for that. And if you really want to have a discussion about that, we can talk about that, but that's a bit too much for this course. Okay. Then you have single subject design. That's also known as single case, small n, NS1 design, etc. You basically test a single participant or subject, like test animal. Why would you do that with human beings? Well, that's a really good question. Some people focus on time series research. Psychology is the science of individuals, really, even though we don't treat it that way because we look at groups, as I've just said, but theoretically. Okay. Imagine you have a very rare genetic disease, though. You may only have access to 1 or 2 people in your environment who have that, and then you may be forced to do this kind of research. So there are pros. Your entire experiment can be conducted with a single participant, which is nice, right? You don't need 30 people per group because there's only the one person. It's really suited for determining the efficacy of a behavioral intervention for that person. Imagine you have a child that is quite severely cognitively delayed, and it engages in self-harming behavior. You're trying to get that child to stop doing that self-harming behavior. You don't need a group for this. You just need to study that child, right? It doesn't matter whether undergraduate psych students stop behavior when you give them that training. You don't care about that. You care about that one kid. And then NS1 research is very appropriate. You may not need statistical tests. Burroughs Frederick Skinner said, I need to eyeball the data. He didn't really like statistics. And basically his reasoning was, if the behavior pattern cannot be seen by the naked eye, your experiment wasn't conclusive. Now, modern scientists would, I think, disagree a bit with that, but it's an interesting viewpoint. So you may not need stats. You just look at the graph. While the behavior goes down, 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 and then it levels off, well, then the behavior is reduced, period, right? And you can attain very precise control over the variables that are influencing the target behavior. You can try to get very powerful treatments that produce really large effects because you're really studying that one person. But of course there are downsides as well. Can you know whether your treatment was truly effective if the behavior does not revert to the original baseline when the treatment was withdrawn? So imagine that you reward a child that we were talking about. You reward that child every time it does not harm itself. But then you stop rewarding. If it then starts harming itself again, that's not necessarily a bad thing. That means your treatment worked. But that does mean you have to keep rewarding it when it does not harm itself. Right? So that can be a little difficult to figure out because there's no control condition. But I'll show you a way you can deal with that in just a second. This kind of research is also not appropriate for situations where the treatment is expected to produce a longer lasting effect. It might not always be helpful because at some point you can't follow someone anymore. You cannot keep following that child for 15 years, typically. That costs a lot of money. It's not doable. And sometimes it's ethically inappropriate to remove a treatment once you have shown that it works. If you have shown that your treatment, your intervention has made that child harm himself less, and you then withdraw that treatment, that's unethical because you know that it was helping the child, and yet you choose to remove it. Okay, so there are some ins and outs here that we need to talk about. How do you then handle these sorts of situations? Okay. Well, there are different things you can do to make this kind of NS1 research better, to figure out whether your behavioral manipulation actually worked. One of these interventions is called multiple baseline design. A treatment is instituted at various points, successive points in time, for 2 or more people or settings or behaviors, whatever it is you're looking at. I'll start with the cons, and then I'll show you a bit more how this works. So basically, one of the cons is you need to have more than one person now, or a setting or whatever behavior that you're trying to apply that treatment to, right? So now you're saying, I start your treatment here, and her treatment there, and his treatment there, right? So now time passes. That becomes more involved. You need to have more people than just the one. Your treatment effect could generalize across different settings or behaviors before the treatment has been instituted for that specific setting or behavior. That's another issue that you could run into. But fortunately, this kind of setup has a lot of pros as well. You don't have to withdraw treatment to determine if it is effective, because you now have multiple baselines. This kind of setup is also appropriate when the treatment is likely to produce permanent changes in behavior. Then it works pretty well. It's also helpful when it could be unethical to withdraw treatment once some improvement has been achieved. And this can be helpful when you're trying to assess the effect of an intervention on multiple behaviors, because you have multiple baselines. Okay, now how does this work? Because I don't think that in your brain right now is very clear. So let's talk about some of these setups, okay? And then hopefully visualizing it makes it clearer. I'm just going to take out my laser pointer again. So here we have a baseline. So let's say that we have that child that's harming himself, right? Here you don't do anything. You just, over a couple of days, you track how often that specific behavior occurs, so that you have a baseline. And then you give the treatment. That would be phase B. So we have A and B. That's why we call this an A-B design. You give the treatment, and as you can see, that self-harming behavior goes down. So now that is a bit more informative than not having a baseline, because now you can actually show the behavior went down with my manipulation. But you can improve upon this. Slightly better, but also more time consuming, is a reversal design, also known as AB-AB. Well, if you understand that this is AB, then you'll understand what AB-AB is. You measure the self-harming behavior in this child, you give your manipulation, well, the behavior goes down. Now you withdraw the manipulation. So if you were reinforcing that child every time it did not harm itself, you stop doing that. And then what you may see is that, look, the behavior goes up again. And then you reintroduce the treatment. You start to reinforce the child every time it does not harm itself, and again, the behavior goes down. AB-AB. This AB-AB design is more powerful than AB, because now you can see, look, there's a baseline, I do my manipulation, the behavior goes down, or for that matter, up, of course. You could also have a manipulation that increases behavior, but in our case, it went down. I withdraw the manipulation, behavior goes up again. I give the manipulation again, it goes down again. This was not a fluke, this was not a coincidence, it's a pattern, right? Statistical law dictates 1's a coincidence, 2's a trend, anything beyond that is a pattern, in my mind. Then you have the 2-treatment reversal design. So now you could have 2 treatments. Let's say that I'll try to stick with this example. You have the self-harming child. You have 2 treatments in mind. One is you reinforce the child whenever it does not harm itself. And treatment 2 is you punish the child when it does harm himself. Okay, I don't want to keep saying it, when he harms himself. Okay, so we have a baseline. Now we do treatment 1. We reinforce the child when he does not harm himself. And you see not much changes in the behavior. Okay, then we try the second treatment. We punish the child every time he harms himself. Now the self-harming behavior really goes down. Now we go back to baseline. We don't do anything. Well, then the self-harming behavior goes up. Now we do treatment 2, because that was the most promising one. And now what do we see? The behavior goes down again when we punish that behavior, right? So that would be a reversal design. We have baseline, treatment 1, treatment 2, baseline again, most promising treatment. Okay. Of course, you can keep going, right? Do another baseline, then yeah. At some point you get A, B, 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 B, A, B design, and then you run out of time and money. Okay, then you have multiple baseline across something design, across persons, different behaviors, different settings. This looks a little complicated, but it's not. So here we have 3 people, A, B, C. We measure a baseline, and person A begins the treatment here. And as you can see, the behavior goes down. As participant A is undergoing the treatment, participant B and participant C are still in baseline, so they don't get the treatment. For participant B, the treatment starts later, and indeed behavior goes down. And for participant C, treatment starts even later and behavior goes down as well. Now you know that your effect does not depend on specific timing. Imagine that you give students an anti-anxiety training, but it happens to be the case that you give that, you have a baseline measurement of anxiety, and you give them all the training, but you give them that training during the exam period, right? And then you measure after the exam period. Well, then probably at the baseline, they were all anxious because their exam period was coming up, but you measure when their exams are over. So now they're less anxious because the exams are over. So now if you give everyone the same training at the same time, you cannot uncorrelate, sort of untangle whether your training worked or whether it was just the passage of time that made them less anxious. And these kinds of designs, where you give people treatments at different times, can help you disentangle those kinds of effects. Okay, and then we have the changing criterion design, which is a slightly complicated one for people to understand sometimes, but it's not as difficult as it seems. Basically, the effect of the treatment is demonstrated by how closely a behavior matches a criterion that you set and that you systematically alter. So let's say that someone is trying to reduce the number of cigarettes smoked. Well, then you first acquire baseline. So on day 1 they smoked, what was that, 17 cigarettes, and then on day 2 16, and on day 3 it was 15 or so, and you get what I mean. And then you set, so now you know, okay, this person on average, well, they smoke about this many cigarettes, and you set a criterion. You say, okay, so you get to smoke 16 cigarettes. And then you measure on consecutive days how many they smoke. Well, this is a little less, this looks like it's 16, this is a little less. Once they can stick to that, they can only do 16 cigarettes a day, you lower the criterion. Now it's 14. You see how well they stick to that. And once they can really stick to that, you lower it again. Now it's 12, now it's 10, now it's 8, 6, until you get to 0. And once they can stick to 0, they've ceased smoking. Pippity poppity, show me the zoppity. Now we're done, right? Okay, so there are pros. A pro of this is very helpful when behavior is intended to change gradually by a specified amount, like say studying. If you only study the night before the exam, you're robbing yourself of an education, right? You have to study all the time, but that can be difficult. So then you set this. I'm going to study 3 pages a day. Until I can do that, then I'm going to study 5 pages a day, or 7, or whatever you think is reasonable. Not going from 3 pages to 20 pages, obviously. But this is how you can increase. Or I want to exercise once a week. Once I do that, I can do it twice a week, etc. And there are cons. It can be a little difficult to determine if the change in the behavior is actually because of the treatment, unless the behavior really closely matches the changing criteria, right? Because, I mean, again, it could also just be the passage of time. There could be all sorts of things going on that have caused that behavior to change. If like this person is smoking and they use that to cope with stress, and then here their mother is in the hospital, they're probably going to smoke more cigarettes, right? For example. Okay. What you can then do to help with this problem is use aspects of a reversal design. So sometimes what they do, and that may sound a little counterintuitive, but if this treatment you are giving is really helping someone to cease smoking, what you should see is that if you go from 12, you say, okay, actually you can smoke 14 again, but they stick to 12, well, then your intervention is helping, right? But if they go up again, then what is really happening? Then your behavior behavioral modification was not very effective. So that's how I would read that. Okay, we're almost there. Animal research. We have to address that because people have very understandably very strong feelings about this, and animals are fun, right? But in this course, we'll see a lot of research with animals. Um, a lot of it very innocent, like pigeons learning how to play ping pong and that sort of stuff. But animal research, it evokes strong feelings in people. So I would say this: there are some advantages. Researchers can control for very specific genetic influences on behavior because they can use knockout mice or transgenic mice or mutated mice. So you know exactly what the genetic makeup of that animal is. They can use cloned animals so they all have exactly the same genes. So you know that changes in behavior are not because of specific polymorphism, specific gene changes, differences in genes. Researchers can also control very precisely learning history. Think of everyone taking this class. I have some second-year students, I have some fourth-year students. You have learned different things because you've been studying psychology longer or shorter, and that's perfectly fine, but that means you have a different learning history. I do not come from Canada. I did my schooling in Europe, so I have a different learning experience from people in Canada, just because schooling is a little different in Europe, right? In animals, you can control that. The animal's born in captivity, you know exactly what it has and has not done. Researchers can, much more strictly than human beings, control the experimental environment for animals. It's not really possible to put people from the day they're born into a little white room and then do all the experiments in there. But with animals, you can. And there is some research that ethically cannot be conducted with humans. If you want to excise a part of an animal's brain, and you have good reason, and that passes an ethics committee, then you may be able to do that. But with humans, you would not be able to do that unless they have to undergo that surgery. Obviously, we cannot just start cutting out pieces of humans' brains. Now, there are cons here. I'm not trying to make this seem to be something it's not. The most cited, the most fundamental criticism is animals have rights. They have rights similar to humans. That's true. But sometimes we need animals to test certain things. I'm not talking about like jamming mascara into a rabbit's eyes to see if it has a reaction. I personally don't think that is necessary. That's my opinion. But when it comes to testing a COVID vaccine or any other vaccine, we start with animals. If that vaccine kills 50% of animals, there's a problem. If it kills 100% of animals, there's a massive problem. You can't start there with human beings. But that's, to me, a different class of research than, like, again, poking lipstick in bunnies' eyes. Know what I mean? Okay. One other disadvantage that people don't always consider, because most people go to cruelty. It's cruel, it's not nice, but I get all that. But an equally important thing is the findings may have limited applications to humans. You're not a rabbit, you're not a rat, you're not a pigeon. So if Skinner found things about learning in pigeons, that need not generalize to you as a human being. Why would it? That's very weird. Is that not weird? Like that doesn't necessarily generalize. Now, of course, if you deal with chimpanzees, with bonobos who have brains that are quite like ours, not the same, but quite like ours, that step is smaller than if you test something on a mouse. And then, you know, so I'll give you one example that I found really interesting, that this is really like cutting edge research. Right now, this is being published. You know what stem cells are, I think? Those are cells that have not yet differentiated, so they can grow into different things. They can grow into liver cells or neurons or whatever. They've recently published a study, and this is really recent, like not like 5 years ago. This is now, coming out now, where they used stem cells harvested from menstrual blood, and those could be used to ameliorate, to improve dementia-like symptoms in mice. This is groundbreaking research. Very early stages. This is with mice. Mice are not humans. But imagine the promise of that research. And also, imagine the use for menstrual blood. Out of the box, someone came up with that idea, but brilliant to harvest from that. Doesn't kill anyone. You don't have to have difficult surgery to harvest those cells. Fascinating. The future is now, children. Okay. Bear in mind that almost every professional organization, RDP has one too now, has a guiding body, a committee that judges the merit of animal research. You cannot just say, I'm going to test this monkey and then I will slit its throat. Sorry to be so graphic, but I mean, then I will kill it and then I'm just going to harvest its brain. I'm going to look. That's not allowed. You have to have really good, and also they would euthanize those animals more humanely than that. But I'm trying to make a point. That kind of stuff not allowed. You cannot do that. If there are other ways to study what you want to study, you should use those methods, right? So it's not a matter of we just sort of torture animals because we think it's fun. That's not how it works. Really not. That's an important thing to think about. But again, this is something people have strong feelings about. And I fully understand and respect that. Okay, so think about what you, I know this is not, like, we're not face-to-face right now, but I mean, think about what you consider acceptable risk ratio for animal research. At what point do you think it's allowed? At what point do you think it's not allowed? Think about it. It's good to give that some thought. I don't know if there was a weird thing there. All of a sudden, my recording stopped. I don't know why. All we have left, I said, was a recording. So you should now be able to use accurate terminology for describing research as well as measurement of behavior. Some of this terminology you know, I'm assuming at this point, independent, dependent variables, you're at least somewhat familiar with. Some of this stuff like A/B designs, that's a bit more complicated, but as we go through the course, you'll become more familiar with it. You should be able to select appropriate methods for measuring the different types of behavior. You should definitely be able to distinguish between descriptive and experimental research methods, but there's a really good chance you're already able to do that, especially if you've taken 2713 or 313. That's fairly basic, but if this was new to you, that's perfectly okay too. We'll cover it multiple times in this course. You've seen how to select appropriate research designs for different research questions or situations. And we have talked about different pros and cons of using animals in behavioral research. And that's pretty much it. So I hope this was useful. I will see you soon. Let me know if there are any questions. Next class, new hat. Bye.